Welcome back. Accelerated Math Analysis. We're getting into Chapter 12, a shorter chapter at that. But we're going to be working with sequences. And the thing is, you've been working with sequences for a very long time. And many classes, maybe even in elementary school, you'd be given a pattern, 2, 4, 6, and you'd say, hey, what's that next number in the pattern, which in this case, I think we'd all agree would be 8. You've seen these types of patterns in earlier classes without a doubt. We're really going to investigate them a lot in this chapter. Our first learning target is that I can write the first several terms of a sequence, and a sequence of a function whose domain is the set of positive integers. So, let's find out what a sub 1 is. That's that a sub n. Write down the first 5 terms. Well, if n is 1, that would be 1 squared minus 1. Well, 1 squared is 1. 1 minus 1 is 0. So our first term here would be 0. A sub 2. Well, that would be allowing n to equal 2. We'd have 2 squared minus 1. Well, that's 4 minus 1. That, of course, would work out to be a 3. If we had our third term, a sub 3, 3 squared minus 1. Well, that's 9 minus 1. 9 minus 1, of course, is 8. And, we're almost done with this first problem. Plug in a 4 for n. 4 squared minus 1, that's 16. 16 minus 1 is 15. And then finally, our fifth term, a sub 5, we'd have 5 squared minus 1. 5 squared is 25, so 25 minus 1 would be 24. Here are the first 5 terms of that sequence. Notice how we're using subscripts to clearly identify what is occurring. We see that a sub 5. It's really indicating it's not just a number in this pattern, but it's the 5th number that we'd have in the pattern. So let's take a look at example number 2. Example number 2, write down the first 5 terms of this sequence. And you can see we've got negative 1 to the n times n all over n plus 1. Well, we'd say, well, what's our first term? A sub 1 would be negative 1 to the 1, and then we'd have 1 all over, 1 plus 1 is going to get you a 2, so you'd have 1/2, but it's going to be a negative 1/2, because negative 1 to the 1 is just going to be a negative 1. How about a sub 2? Well, this would be negative 1 raised to that second power. You can see we're using this formula, and then n is 2 down below, we'd have 2 plus 1. Well, negative 1 squared, of course, is positive, and we're going to have a positive 1, and then that's a 2 over 3. Continuing on, we could say, what about our third term? Well, that's negative 1 to the third, and then we'd have 3 all over. Well, 3 plus 1 down below, 3 plus 1 is going to get you a 4. But once again, negative 1 to the third here, this is going to be a negative 1 times 3/4. We're left with negative 3/4. A sub 4, well, we've got negative 1 to the 4th times a 4 over 4 plus 1. Any even power that we're raising negative 1 up to really becomes a positive, and we're left simply with a 4 over 5. Last one, a sub 5, well, we'd get negative 1 to the 5th times a 5 all over 5 plus 1. What are we really seeing? Well, negative 1 to the 5th is something negative, and we'll be left with negative 5 over 6. So we're seeing that this sequence alternates. It alternates between positive and negative values, and you can see that the numerator and denominator are always one step apart. The denominator is one step bigger than the numerator. Okay, our second learning target is that I can write the terms of a sequence defined by a recursive formula. Actually, that's not even what we're getting into here. For example 3, a recursive formula is something a little bit different. I'm going to have to tell you about that. This is simply working backwards, however. We're really saying, look, what if we gave you a whole bunch of terms? So this is a different learning target. We could say, given a sequence, I could find the formula that defines the nth term. So try to find a sub n. You can look here. Here we have our first term, our second term, and our third term, and so forth. Look at the numerator. We have a 2, a 4, an 8, a 16. It doesn't take too long for students to realize that those numerators are all powers of 2. They're powers of 2. So we would guess that a sub n would be a 2 to the n. So for our first term, we'd have 2 to the first. Second term, we'd have 2 to the second, and so forth. But look down below. These are all powers of 3. 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. So we could certainly write it as 2 to the nth all over 3 to the nth, or equally, we could have written that as 2/3 raised up to the n if we would rather. So that's some food for thought right there. Let's take a look at example 4. For example 4, my goodness, as we're looking here, you can see that, for our first term, we have a 2 in the denominator. In fact, we're going to have a numerator of 1 for every single one of these. But then you come over here to our second term, and we have a 6. And then for our third term, we'll have a 12. And for a fourth term, we'll have a 20 down below. And you can begin to wonder if you see a pattern here. Well, rest assured, this pattern definitely seems to be way more complicated than some of the others. Perhaps we're not seeing obvious powers of a number. You look at your 2 and your 6 and your 12, it's not as if we have 2 to the first, 2 to the second, 2 to the third. As we begin to wrestle with this, sometimes these become very interesting puzzles. What you might begin to think about is also, first of all, notice that, between 2 to 6, you would add a 4, but you wouldn't be adding the same fixed value of 4 to get to your next number of 12. 4 plus 6 is not 12. Likewise, you don't seem to have a consistent multiplication rule, like 2 times 3 is 6, and 6 times 3 would then be 18. So, if you have that, perhaps you could, think about a formula that might be occurring. But looking at squares can be very, very helpful. Off to the side here, I just want to say that your first square, 1 squared is a 1, 2 squared is a 4, 3 squared is a 9, and 4 squared is a 16, and 5 squared, you get the idea. Of course, right here, kids can very, very quickly realize that that's not the denominator pattern that we're seeing. We don't start with a 1 in the denominator, then a 4, and then a 9, and a 16, and then a 25. However, if you did have a 1, how would you then go up to a 2? Well, perhaps you'd say, well, I guess I would add a 1. This is if n were to equal 1. What if you were over here with 4? What would you add to get up to a 6? Well, it would be a 2. Look at that. 4 plus 2 would be a 6. This is where n is equal to 2. Look, 3 squared is 9, but if you add a 3 to that, you would then arrive at a 12, wouldn't you? If you had n is equal to 4 and you have 4 squared is 16, well, guess what you could add then? The n value of 4. That would lead up to a 20. 5 squared is 25, but if you add that n value, you would actually get 30. So what might we guess that we have for this pattern? This one was really thought-provoking, truly a real brain buster of a question right there. But it opens up the door to help you realize that maybe looking for squares or perhaps even later on cubes, and investigating if you're just adding a constant there, perhaps that very well could help you. Well, let's take a look at number 4, example 4. My word, you've got your first term. You've got your first term right here. Then you've got your second term. Look at that. Second term gets flipped upside down. Your third term is not. And yet your fourth term, you are flipped upside down. Likewise for your sixth term. And it doesn't take too long for students to realize in this very strange pattern that even numbered terms are really having a reciprocal of that numbered term. So if I went out to the 10th term, I would expect to see 1 over 10, whereas the odd terms are just that odd numbered term itself. So the third term is 3. The fifth term would be a 5. Sometimes kids are even wondering, is it possible to come up with such a thing as that? Yes, definitely. We can say n if n is odd, and 1 over n if n is even. Very, very strange way to write that out. Sometimes, surprisingly, you don't have a nice, singular, concise formula like you saw in example 4 or example 3. But all the same, this is really how you could work that out. Now, factorials, something that you've seen before, that little exclamation mark, really means that we can take, for example, if I gave you 5 factorial, would say take that integer, that positive integer 5, and multiply by 1 step below 4 times 3 times 2 times 1. See, that's what n factorial in this form is really saying. Start with integer n, multiply by 1 step below, multiply by the integer 1 step below that following integer as well, and continue to do that until you arrive at 1. So, for example, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So in this section, we very well will see factorials come into play. Let's take a look. This is really our second learning target when we were talking about recursive sequences. Let's read this definition together. A sequence that is defined by assigning an initial value, a beginning. That's really what we have for our word initial. Initial tells us to begin right there. And then specify an nth term by a formula involving one or more preceding terms. That's what is known to be defined recursively. For example, in example 5, we're told that a sub 1 is 2, and then they're saying a sub n is simply n plus 3 times a sub n minus 1. So they're saying write down the first 5 terms. Well, we already know a sub 1 is 2, but now we're going to follow this formula here. I'm going to let n be 2, so a sub 2, if I'm going to let n equal 2, it should equal n, which is 2, plus 3 times a sub, now n minus 1 here would just be a 1. So the term that I just found, I'm going to use in my calculation of a sub 2. 3 times 2 is 6, and 6 plus 2 is 8. So I've got a sub 2 is equal to 8. To do a sub 3, I will do n, which is 3, plus 3 times a sub 2. Because if n is 3, n minus 1 is 2. So a sub 2, I just found a moment ago, it's 8. And 3 times 8 is 24. 24 plus 3 is 27. Hopefully you get the idea. A sub 4 would be 4 plus 3 times a sub 3. A sub 3